Hey guys, welcome back. My name is Mr. Kim. I am going to go over the 2025 AP Chemistry FRQ question number 6. A scientist constructs a galvanic cell as shown in the diagram. As the cell operates, zinc electrode increases in mass, increases in mass, and the aluminum electrode decreases in mass. Okay. A data table of the standard reduction potentials for the substance are shown in the diagram. Write the half reaction for the oxidation that occurs at the anode. So we're looking for anode, we're looking for oxidation. So let's go. We're looking for oxidation that's occurring, which means that the solid electrode is actually turning into aqueous ions, right? So that would be the one in decreasing mass. So we know that aluminum says it's decreasing in mass, whereas zinc, its mass is increasing, so it's getting built up. So we know that this is the oxidation, and we know that this is the anode from the red cat sat on an ox. So what we want to do is we want to write the aluminum half reaction, but write it in reverse because this is a reduction potential. So let's go ahead and do it. So what we're going to write is we're going to write aluminum solid oxidizes into aluminum 3 plus aqueous plus 3 electrons, and that is the answer to A. Part B, write the balanced net ionic equation for the overall reaction that occurs in the galvanic cell. So we know that we got the oxidation half reaction, and all we have to do is just carry over the same zinc. But what we do have to understand is that there is a discrepancy between the electrons, right here. So therefore, what we need to do is we need to go ahead and multiply the top by 3 and bottom by 2. Okay, so there goes some changes. Now, what do we know? Then the electrons will be 6 each. I'm just going to do my math over here. And then getting rid of this, right? We can go 3, 3, 2, and 2. So what happens? See, when you flip this reaction backwards, the electrons drop out. So therefore, what you're going to end up with is going to be what? Let's write the oxidation side first. It's going to be 2 aluminum, right, reacting with 3 aqueous zinc 2 plus ions, yielding 2 aqueous aluminum cation plus 3 zinc solid, and this should be the answer for part B. Let's go to C. Initially, each electrode has a mass of 50 grams. The cell is allowed to run for a period of time and then stopped. Which electrode's mass changed the most? Justify your answer with calculation. Now, there are many ways to do this, right? But I think the way that I'm going to choose to do it is essentially, I guess you could try to start with the 50 grams and convert to number of moles, but I think that's unnecessary. We do know that in 1 mole of reaction, you get 6 moles of electrons, right, exchanging hands between the anode and cathode for every 1 mole of reaction. So that's one of the things I'm going to use. So let's get started and do the calculations, right? So it says which electrode mass changed the most. I'm going to leave some space so I can write that down, but I'm going to do the calculation on the bottom. So let's go ahead and do it. So now we're going to start with a zinc, right? Your zinc electrode. So we know that it's 6 moles of electron. Let's say if we put through 6 moles of electron, right? It's per 1 mole of reaction, right? So what do we know? In the reaction stoichiometry, you get 6 moles of electrons exchange hands for 3 moles of our zinc, right? And that's right up here, right? 3-to-6 ratio. All right, times, and then what's the molar mass? It's according to our reference table is 65.39 grams per 1 mole of zinc. All right, so that should give us a value of, and what do we know? 196.2 grams. And what do we know about zinc? Zinc is reducing, right? Grams created, right? And then what else we got? We got our aluminum, which again is going to start with 6 moles of electrons per 1 mole of reaction. Oh, by the way, I really should cross things out, right? So what do we know? We got this, we got this. So that gives you, in the end, grams per mole of reaction, right? Right. So continuing down here, what do we got? Down here, however, for the aluminum, we understand the ratio is going to be what? For 6 moles of electrons, it's going to be 2 moles of aluminum, right? So it's going to be 2 moles of aluminum created for 6 moles of our electrons, right? And the molar mass is going to be 26.98 grams per 1 mole of our aluminum, right? Okay, and crossing things out, we get gram per mole of reaction, do we not? And that should come out to 53.96 grams per mole of reaction that is lost. Right now, we're looking at delta M, the amount that changed, right? So we understand that the zinc electrode mass changed the most. Okay. All right, so that should take care of part C. Let's go on to part D. All right, so looking at part D, what do we notice? Well, for part D, it's the standard zinc aluminum cell has a value of the total cell potential equal to 0.90 volts. The scientist needs a galvanic cell that produces a greater voltage. The scientist has access to the chemical systems in the table. If the scientist uses zinc half cell and one of the other options from the table, what is the maximum voltage that can be generated from the standard conditions? All right, so there's 2 ways looking at this, right? So we are fixed with zinc as one of the half cells, right? So the zinc could actually be the anode or the cathode, right? So let's look at 2 different scenarios, right? The 2 different scenarios is zinc as the anode. Well, actually, since it's in reduction half reaction, let's just go ahead and make it easy and say zinc as a cathode, right? So zinc is reducing, which means that what's going to happen is it's going to be, it's going to stay the way it is, right? And then what's going to happen is, if this is going to stay where it is, the other extreme would be what? It would be finding a negative value that's going to be, well, essentially what I'm going to do is we're going to have to flip one of them, right? So if the zinc stays as reduction, that means that this value of negative 0.76 is going to stay, all right? So what's the other way to look at it? That means that we're going to look at somebody that's going to oxidize. Well, since this is the reduction potential, that's if zinc is reduction. So to look at it, we're going to look for somebody that is even lower reduction potential, right? And what do we got? We don't really have much, right? So this is not going to work out. So the other way to look at it is, what if we have zinc that's going to oxidize, right? If zinc needs to oxidize, that means that zinc must have a lower cell potential, right, than somebody else. Well, you know, this is a much higher cell potential, isn't it, right? So therefore, what happens is that if we pair it up with gold and zinc, then what do we got happening? Then we know that gold, having higher reduction potential, will go ahead and reduce, right? So it's going to be such that gold will reduce and zinc will oxidize if you pair it that way. So in that case, what's going to happen? Gold, that's an AU, is going to keep its half cell potential. And then what's going to happen to zinc? Zinc is going to have to reverse, right? Its cell potential. And essentially, in the end, the total cell potential is going to be the sum of these two, right? So in this case, if you do that, you end up with a 2.26 volts, right? Now, going back to this, I was too quick to be dismissive, right? So let's go revisit this for a second. If we go revisit this for a second, you'll understand that it still doesn't work out because why? In another case, right? So this is the correct one. But the other way to look at it would be what? If zinc is left to reduce, what does that mean? That means that the negative 0.76 has to be the highest reduction potential, right? So that means that we're going to have to find a loser that's going to have to oxidize in this chart, which means you have to pick the lower or the lowest, which would be in this case, right? So if we paired it up like this, then this would actually have to oxidize and this would have to reduce, right? So that's the other extreme you can get. And let's see what happens over there when you do that. Since this is being oxidized, then that means that this is going to have to switch over to positive 1.85, right? And then zinc will stay the way it is. It's going to be negative 0.76, right? And if you take the sum of these two, you're not going to get a higher voltage, right? Because it's essentially going to be what? 1.85 plus negative 0.76. And that's going to give you what? Something barely over 1 volt. So that's why we know that this is not going to work. Okay. So like I said, what I did was that I picked the zinc and then I put two scenarios where in one case it's going to oxidize, one case it's going to be the reduction, and find the appropriate partner and figure out what happens, right? So the proper answer is this one. So let's go back and answer this. What is the maximum voltage generator? Okay, so they didn't actually ask you what you're going to use. So you're going to write, excuse me, you're going to write the maximum voltage is 2.26 volts. Okay. They didn't really ask for work either. So essentially, this would be more than enough to answer this question. And that is the conclusion to question number 6. I hope this was helpful to someone. Thank you for watching.